Hello and welcome back to AP Pre-Calculus. Today's lesson is 1.9 and 1.10, rational functions and their vertical asymptotes and wholes. Okay, so as you remember, a rational function is just a function that has a polynomial function in both the numerator and the denominator. And we're going to have, since we're going to have x's in the denominator, there's going to be chances to get zeros. Sometimes when we input our domain, we might get an output of 0, and we cannot have zeros in the denominator. And if we do get a 0 in the denominator, it ends up being one of these, either a vertical asymptote or a whole. All right, so let's start out with wholes. Over here on the left-hand side, you can see these two equations, my f of x and g of x functions down there. If you notice, I have the same factor in the numerator and the denominator. So on the f of x function, those would cancel out, leaving me f of x equals x plus 2. That's the simplified function. It is not the actual function. The actual function would be all of that stuff before I canceled it out. Meaning, when I start substituting in all my domain numbers, when I get to 1, if I didn't take 1 out of the domain, I would create a whole. I would end up getting a 0 in the numerator and a 0 in the denominator, and we can't have that, right? We can have zeros in the numerator, but because the zero's in the denominator, we have a problem. But since you have 0 over 0, that's what creates a whole. On g of x, 2 of my x plus 1s would cross out with 2 of my x minus 1s would cross out 2 of my x minus 1s on top, leaving 1. And we could rewrite this one if we wanted to, 1/2 x minus 1, right? So that would also, the original function would create a 0 over 0. So we've done all this back in Algebra 2. But the new stuff here is, if you look at the graph, if you look below it, you'll see that we start writing our limit statements. Okay, so look at that graph. You see the hole there? Let's go ahead and make this a little bit bigger so everybody can see. All right, hopefully we can all see that now. We have a hole right here. If you look down, it looks like there's a hole at 1. All right, so that means whatever my original equation was, if I would substitute 1 into the original equation, I get 0 over 0. But if I cancel out and get the smaller, the condensed version of the function, if I put 1 in, I'd get 3, even though there's something not there, right? So that's why we would call that a limit at 3. So what this is saying down here is this is saying the limit of f of x as x approaches from the left, because that's a negative, I'm coming from the left-hand side. So I'm coming from the left, I'm approaching 3 as I get to 1. And this one over here says the limit of f of x as I approach 1 from the right. So I'm coming this way. I come to 3. See, both limits from the left and the right are ending up at a number. So this is how we would write a limit statement for a whole. Okay, so let's look at the other side, vertical asymptotes. So vertical asymptotes have one of the same things that a whole does. We're going to get a 0 in the denominator. The difference is we're going to get a regular number. Not that 0 is not a regular number, but any other number other than 0 in the numerator with a 0 in the denominator makes a vertical asymptote. Okay, meaning if you can't cancel out the factor in the denominator with a factor in the numerator, you're not going to have a whole. So here on the first one, this x minus 1, nothing to cross out with, I'd have a whole at 1. The second one's a little bit weird because I do have something that crosses out. So you might think that that would give me a whole, but I still have an x in the denominator. And so it's almost like I have a whole at 1 and a vertical asymptote at 1. You can't have both, right? And vertical asymptote trumps the whole. So you would have a vertical asymptote. Okay, so when we do limit notation of a vertical asymptote, it's pretty much the same idea, right? Look down here. I'm going to approach 1 from the left. So I'm over here and I'm coming from the left. And what is my graph doing? Well, as it gets closer and closer to 1, I'm getting closer and closer to negative infinity. And if I'm going to approach 1 from the right, I start going up to positive infinity. So this would be the limit notation for a vertical asymptote. All right, let's give this a go. So we're looking to see what we have down here, whether we have a whole or a vertical asymptote. Remember, a whole is 0 over 0, meaning we can cross out a factor on both the numerator and denominator, and then a vertical asymptote would be, we can't cross out on top and bottom. We still have an x in the denominator that could cause a 0. So look at A. I have two factors on the top, two factors on the bottom, and I can cross those guys out. So that means I have a whole. We're not going to say a whole at -3. We have to say a whole at x equals -3, right? So that means the actual, what if I wanted the point of the whole? Well, let's see what we have left over after we cross these out. We have f of x equals x minus 2, x minus 5. So if I take that -3, my input, and I put it in there, I'm going to have -5 on the top and -8 on the bottom, so I get 5/8. So that's where my whole is. So that covers our whole, but I still have an x in the denominator, so that means I have a vertical asymptote. So where is that going to be? Well, set your x minus 5 equal to 0, and you're going to get x equals 5. Do not write vertical asymptote at 5. It's x equals 5, okay? All right, let's move on to B. All right, so B is a little bit tricky because there's a lot of things that we could cross out. So I would suggest doing one factor at a time and then naming it, and then we're moving on to the other factor. So I'm going to start with the x plus 1s. This x plus 1 up here would cross out with one of these x plus 1s, leaving one left. So is that going to be a vertical asymptote or a whole? Well, there's a x left in the denominator, so that would be a vertical asymptote. So I'm going to say vertical asymptote at x equals -1. All right, but what about the x minus 2? That crosses out with one of these, and I still have an x in the numerator, so that's going to be a whole. All right, so we got a whole at x equals 2. What's my leftover? I have y equals x minus 2 over x plus 1. So when I substitute this in, my whole is going to be at 2 comma 0. All right, let's give C a try. All right, with C. Now, this is going to be something you might want to do all the time, is to always factor your functions. That'd be a lot easier. So I'm going to go ahead and factor this, and I can take out a GCF of x. I get x squared plus 4. That may look like it can be factored, but it can't, okay? So let's go ahead and give it a shot. Do I have anything that can cancel out in the top and bottom? No, so there are no wholes, but I still have some x's in the denominator. So I'm going to set these equal to 0. So I have a vertical asymptote at x equals 0. That was easy. What about x squared plus 4? If I set that equal to 0, and I square root both sides, I'm going to get the square root of -4. And remember, square roots of negatives give us i's, which these are imaginary. So that doesn't actually create a vertical asymptote. So my only vertical asymptote is at x equals 0. All right, so now we're going to write some limit statements, whether we're going to write a limit statement for an asymptote where we go to infinities, or for a whole where we go to a point. Okay, so let's go ahead and start looking at A. It's already factored for us, which is nice. I don't see any factors that are the same, so we don't have any wholes, but I have an x in the bottom, so I know I have a vertical asymptote at x equals 2, right? So what I'm going to do is I'm going to write limit of f of x as x approaches 2 from the left, and the limit of f of x as x approaches 2 from the right. What do they equal? All right, so this is where we got to figure something out here. So what we have is we have this graph, right? At 2, I have this. And I know this graph has to do something like this. It has to go, it might go like that. It might go like that, right? Like, it's going to go towards an infinity. Heck, they might both go up, they might both go down, but it's got to do something like that. So how are we going to figure out what it does? Well, we're going to look at a point on this side of the line and a point on this side and see where they are. So we don't want to choose any number to the left of that red line and any number to the right of that red line. We actually want to choose a number that is super duper duper close, because the closer I get to that line, the closer I'm getting to an infinity. So if we could figure out what we're doing, it's going to be a lot easier. So what's a number that's just to the left of that red line? 1.99999, like a whole bunch of nines, right? So let's go ahead and see what happens if I put it into my equation up here. If I put a 1.99, that's going to be positive. That's going to be positive. So let's write that down. I got positive times positive. Now if I put it in the bottom one, 1.999999 minus 2, it's going to be a negative, but it's going to be a really small negative, right? And remember, the smaller your denominator, the bigger your number value is, right? So this is going to be a negative big number. So I look like I'm going towards negative infinity. And if I do, on the other side, if I do 2.000001, my numerator is going to be positive. My denominator is going to be positive, but really small. So I got 3 positives. It's going to look like this, boom, over a really small number. And that's going to give me positive infinity. So you want to pick a number on the left and the right of your vertical asymptote, but not any number. So a number that's super duper close. That'll help you out figure out if I'm going towards positive infinity or negative infinity. All right, let's look at this next one. All right, we're going to erase some of this so we have some room. So remember, we're looking to give me the limit as x approaches 2. So we're going to do the same thing. Limit of g of x as x approaches 2 from the left. Limit of g of x as x approaches 2 from the right. All right, so it's all factored up for me. I can actually cancel things out this time, which means this time it is a whole at 2, right? So I should be equaling a number, not a infinity, okay? So all we have to do is take the 2, put it into the equation, and I'm going to get 6 over negative 1, and that's going to give me negative 6. And they have to be the same number if it's a whole. So there you go. All right, we have our limit statements written. Let's look at our function. I have x minus 2's on top and bottom, but I have more on the bottom, so that's still going to leave an x minus 2 down there, which means I have a horizontal asymptote, right? So we're going to do the same thing that we did before. I'm going to use 199999999. I'm going to put it in, and I get a negative on the top, and then I get a negative and then a positive on the bottom. That's going to give me a positive, so that's going to be infinity. If I do 2.00001, I'm going to put it in. I get a negative on the top. I get a positive for the first one and a positive for the second one. And I get negative, which is going to give me negative infinity. All right, they're changing it up on us here. Now they want us to write a rational function that will meet these limit properties that they gave us. All right, so the first limit property is x is approaching 3 from both sides. And as we do that, we're coming to a point. We're not going to infinity, which means this is a whole, meaning at 3, they have to cancel out on top and bottom. And remember, to put your 0, the 3, back into a factor, you change its sign. All right, so I have x minus 3 is on top and bottom. And then at 1, I'm hitting the infinities. Well, when I hit the infinities, that means it's only in the denominator. So I put 1 back in, and I get x minus 1. But let's go back to this 5, right? So if these were gone, I need to make a 5 when I put in a 3, right? So when I put a 3 in the x in the denominator, I'm going to get 3 minus 1, which is 2. What number divided by 2 would give me 5? We have to have a 10 up there. Of course, like if we were wanted to be fancy, we should write it like this. So there is our function. Okay? Let's go over here to b. So now we have another f of x. It's going to be a fraction. And I have, as I approach -2 from the left and the right, I go to a number. I go to 4, which means these factors have to be in top and bottom. Change the sign. It's +2, +2. All right? And then as I approach -1, I'm going to infinities. So that's only in the bottom. But I want you to notice what's different about a and b and my infinities. In a, we're going to opposite ones. In b, we're both going to positive. We could both go to positive, both go to negative. When that kind of thing happens, when they go to the same side, that means your factor was probably squared. That's why that one's a little bit different, okay? So again, we need to come up with a number. As I'm approaching -2, I should say, I should be at 4, okay? So remember, we're crossing these guys out. They're not there. I put a -2 there. -2 plus 1 is -1. -1 squared is 1. What over 1 would give me 4? We could put a 4 up there. And if you wanted to rewrite it, you could, but you could leave it like that also. All right, so example 4, they want us to sketch a picture. And this time they didn't give us limit notation. They gave it to us verbally. And if you remember from the beginning of the year, there's like 4 different ways we're going to have to approach things, and verbally was one of them. So let's go ahead and make a graph for both of these. All right, so what's going on here? Let's see. We have a hole at 1, so I'm going to have to put a little circle on my graph. As x approaches 4, okay, so 4 is a deal. We're going to increase or decrease without bound, which means we have a vertical asymptote, right? So if we call that 4, so let's see. As I'm coming from the left is this way, obviously. I'm increasing without bound, so I have to go up, right? So let's go ahead and graph that. Something a lot like that. Now, I do have a little bit of an issue here because I forgot my hole, right? So right here at 1, I could come up here and put a hole. You could have put the hole first and then done it, but that'll be fine. And then as I approach from the right this way, I am decreasing without bound. So it has to look something like that. Okay? Let's look at B. I have 2 holes. I have a hole here at -2. I have a hole here at +3. At -1, it looks like I have some asymptote idea here. So at -1, put my asymptote. All right. Both of them are decreasing without bound. All right. So I can come this way. Oop, let's go back to black. Come this way. If you want to do this, watch it. Oh, boom. And then I'm coming this way. Boom. And it looks something like that. Okay. So let's go back a minute and see if we can write the functions here, or a possible function. They didn't give me enough to really go because they didn't tell me what my value was at the hole, but I know I have a hole at 1, so I can do x minus 1 and x minus 1. I have vertical asymptote. They're going in opposite directions. Vertical asymptote means that it needs to be in the denominator, and it was at 4, so x minus 4. Since they're going in opposite directions, we're good with that. What about the second one? This time I have 2 holes. So I'm going to put x plus 2 and x plus 2, x minus 3 and x minus 3. And I have a vertical asymptote at -1, so x plus 1. But they're going in the same direction, so I'm going to put a squared. Since they're going down, probably need a negative somewhere. So we just put it out here. You can put it at the top. You could put it out front. It's poorly written because I ran out of room, but you get the idea. And to be honest, if you look back at A, seeing that if you go from left to right, you notice how that's going down. That also gives you an idea that we probably needed a negative over there too. All right.